Excellent. Wow. Well, thank you for coming back from your coffee to hear about things you didn't know. My name is Steve Poole. I'll give you a better picture of me. I've been doing Java since before it was one, so I've literally been working on Java 25 years. I don't really do JVM stuff anymore, but I used to design them and code them and debug them and performance tune them and all that sorts of stuff. So I have a lot of background in JVMs. Used to work for IBM doing all that. Then went to Red Hat for a bit, and now I'm here. Anybody recognize this? No? Yeah, maybe. Okay. You recognize this, though. Maven Central. Sonotype, company that produces Maven Central. And a bunch of other things that you may or may not notice, like Nexus and stuff like that. Now, I'm at Sonotype because they're basically a secure supply chain company, and I care about security. The thing that I'm really passionate about is helping you produce safer software, in whatever that means, whether that's how you develop or the tools you use or what knowledge you have. And Sonotype are very kindly letting me do that. So I'm not going to talk about something. I'm not going to talk about Security Manager. You may have read in the abstract that it's about Security Manager, and somebody said, oh, I'm looking forward to hearing a talk about Security Manager. Who's used the Security Manager? Anybody? No, you just don't admit to it, okay? The Security Manager has been deprecated. It was only around from the beginning for applets and things like that when we were downloading code from the web, and it was pretty much a disaster at the time, and it never got any better. There are some obvious replacements, which again, I'm not going to talk about. Well, maybe, right? But there is a reason for that. Now look, I'm going to give you a slide with a bunch of words on. And I know you're going to read these. But what I want to get across, and we're going to go into this, is that the reason that we can take things like the Security Manager away is that we have a really good design. The JVM is amazing from a security point of view, and it's kept up to date. There's all sorts of wonderful encryption protocols, communication protocols, blah, 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 and a fantastic design, which is what I want to talk about. So I know you haven't finished that, but who cares? So this is what I want to talk about. I want to take you through why I'm even talking about it, give you some ideas about the challenges we're facing, look at the types of attack that bad guys apply to us, maybe dispel a couple of myths as we go along. I haven't got a section, we'll just do that as we go. I need to explain to you about the JVM. So much of this is about how a JVM works and the bits and pieces. A little touch, if we have time, about some other things. And then there's a couple of secret weapons I want to talk about. And then we'll finish. Okay. So let's start with the most important thing. What's the point? Cybercrime is this horrible thing. It's been around for some time. 2016, a few years ago, cybercrime, the whole cost of cybercrime, was about the same as the drug trade, that illicit drug trade. You know, all those, you've seen all those movies where people are burying money or weighing money by weight. And at that time, it was about $450 billion, which got you 50 of the biggest aircraft carriers in the world. Not sure you do with 50, but that's how many you could buy. Fast forward. Drug trade, 450 billion. Cybercrime, $6 trillion. Not 50 aircraft carriers, 620 aircraft carriers. And just to put that in context, if you were to count up all the fighter jets that you have on 620 characters, 85,000. 85,000 fighter jets. That's what you get for your money. You can see why this is very lucrative. If you put it in terms of GDP, cybercrime would be the third largest country in the world. Okay? Think about that. That's how much money is floating around. Okay? And it's been growing ever since, 50-something% a year on year, and it's not got, there's no sign of it stopping. Right? It's just going through the roof. There's a lot of things happening, which we haven't got time to talk about, in terms of trying to deal with this problem. So there's lots of stuff coming down, and I'll touch a little bit on it. But you have to understand this is an existential threat. Everybody, governments, others, are all going, we have to deal with this. So you, as developers, have responsibilities, which you may not have thought about, and we'll cover those as we go on. Because it's getting bad, right? If this guy is in the movies, he wouldn't do drugs anymore. He'd just do cybercrime. You never get caught for cybercrime, you make a lot more money. The thing you have to understand is, how does this work? What does cybercrime and software have to do with each other? Well, it's all about open source. These bad guys primarily want to use open source against you. So everything that you choose, the software, the downloads and things that you choose, are all potential vectors for getting into your system. 90% of your application that you've written, the other 90%, the frameworks, everything, even the operating system comes from somebody else. So 90% of your application was written by somebody else and is shared by somebody else. And that's what they're after, right? It's all about getting into open source projects. It's looking at open source projects, figuring out how to compromise your systems through those open source projects, and whatever vulnerabilities they can do. And it's exploit first. You used to have time. When a vulnerability was published, you'd have time. You don't have time anymore. These bad guys are creating their own exploits. They are using them before they even get published. So when you hear about a vulnerability, like Log4Shell, for instance, you have no time. The clock has already started ticking. You're already vulnerable, and many people would have been attacked. So now I want to boil this down and say, well, what are the attack vectors that we care about? What's the JVM piece in this? Okay. So we need a picture of what a JVM looks like. I tried to find a picture from my old days, and unfortunately all I've got is paper. Lots of design books of JVMs, so it's all paper. So I had to draw a quick one. But there's a bunch of stuff. It's quite structured. You look at JVM design, they're all pretty structured. They're all very similar. You have just-in-time compilers. You have the JVM. You have a bunch of native code, classes. You know these things. And then there's class loaders for loading classes off the disk or off remote systems. And then on top of that is your application, and of course all the dependencies that you've brought down. So, squint at it, and this is everybody's life. Okay? So you might think that one of the things that they would try and do is break your communications. Can I get into the data streams? Can I read your data as it goes backwards and forwards? Theoretically possible, but pretty much covered. If there's one thing the JVM and the JDK has, is a whole raft of ciphers and encryptions. It's not a big deal. That's not really a weakness. What about the other end? What about where your application, your JVM and your stuff, hits the operating system? What's the security in that space? How easy is it for the bad guys to compromise your environment, and what can you do about it? Well, it turns out that lots of people think it's not a problem because they assume that if any bad guy can get into, can change a single file in your running system, that they have full access. And that's a complete myth. Don't ever believe that. There are lots of vulnerabilities out there that let you access individual files, sometimes very specific files. Right? So it is possible for you to have a mostly secure system, and there's a vulnerability that lets people get into the config files. And that's a classic. So they can do that. And of course, what they're going to try and do is change your change your config. And they've got lots of ways of doing that. Because unfortunately, because actually there's not much we can do about it, the JVM will assume that environment is safe. It's your problem to provide the JVM with a safe environment to run in. So the JVM doesn't do anything other than basic validation of these things to check that they're okay. Right? So, okay, so where do we have better defenses? Where do we do things? Well, what the other attack vectors you have, stand behind the desk, is things you might think about. So, can I change bytecode? Right? We all compile code. Can the bad guys do that? Can they get in and corrupt your objects? What about loading code? Can they get in there and change those? Can they affect the code that you load? Can they force you to load other code? These are more likely attempts. This is the sort of thing that the bad guys are going to try and do because, I said, the environmental stuff, that sort of life, they're not going to, the breaking communication protocols is a different story altogether. So these things, how do I get into your system? So to answer this, we need to talk about what a JVM looks like. So I have words, this is from Wikipedia, but it's a virtual machine, Java virtual machine. And it's got more than that, right? It allows dynamic and secure execution of remote code. Okay. Produces separate environments. Cool. So it knows where the code's from, keeps them safe. It's in a portable and predictable way because it's a virtual machine and it runs on how many operating systems, how much hardware, so much stuff, right? Right. The biggest number I ever had to manage when I was leading one of the teams was 22 platforms. And we had basically the same code running on all those platforms. That's how good the JVM design is. It takes these sorts of horrible pictures of all the different components, whether it's hardware or OSs or file systems or Windows managers or networking, whatever it is, the JVM's job is to take all of that difference and turn it into sameness for your application. Right? So that's why we have these structured abstractions, because we're trying to figure out how's the best way to do that. And so we have a really simple model, right? Operating system, JVM spec, native code and JITs to translate the model into reality, and I know, memory model, CPU model, and a threading model. Well, you might think that, but that's not quite true. Because actually, as far as the JVM is concerned, there's no memory model, and there's no threading model. They're all added on extras. They are sort of unspecified, which, as you'll see, is going to turn out to be a good thing. So as far as the JVM is concerned, things are just objects, and there's an idea of critical sections. You know, don't interrupt these things happening. They will happen in one go. And a really, really simple CPU model, stack-based, because we're trying to take every single architecture and turn it into the lowest common denominator, which is stack-based. Okay, so what's the magic? What's the security in this space that keeps you safe? Well, so the first thing to take away is that abstraction, that simplification, keeps you very safe. Because by definition, it's impossible to get at things that aren't part of the specification. You can't get at threading if there's no threading. You can't get at the CPU if there's no CPU, etc. Right? So there's one register in a JVM, and that's called the program counter. There's no other registers, and even the program counter you can't affect. Registers don't exist. You can't do nasty things. You can't move, force different sorts of execution. And there are no pointers. Obviously, Java has no pointers, But the spec doesn't have pointers either. There's no way of wandering around memory. The JVM doesn't let you do that because the idea of the heap isn't really a JVM thing. It's sort of added around the outside, right? So it's basically class files and object references and obviously something to run the bytecode. So there's your first line of defense. It's really hard to compromise a really simple machine if it hasn't got the usual sort of weaknesses. Now the second line are these extras. So we have a threading model, which is sort of added in. I encourage you, if you want to know this, go look at the JVM spec, and you'll see the JVM spec says, this is not what we do. This is not our problem. And then you'll find the JLS, the Java language spec, will fill in some of the gaps. And it'll also say things like, this is not our problem. All right? And you can track this stuff through, and you'll find that at some points, the specification for what the behavior is way up in the classes. Right? That's really good. So having things like garbage collection, moving objects around, means it's really bad for it's really hard for the bad guys to find the object that's got your password in, because it moves. And anyway, you can't get a pointer into the heap, and even if you could, which is theoretically possible, the objects move. So it's really hard to get inside a heap and do mischief the old-fashioned way. You have to figure out how to get in it using Java. So how do you use Java against itself? Right? And with threading, again, with threading, there's a leaky abstraction which was there from the beginning, but because these virtual threads, well, before we called them virtual threads, had to connect with real threads, and there was some design principles that said I need to be able to access native stuff. Now that we have virtual threads turning up, even that hole's gone. So with total virtual threads, there is no way for you to get at real threads, and if you can't get at real threads, you can't escape. So these two designs are big defenses in how Java is secure. But there's more. The just-in-time compiler, the compiling bytecode to machine code. Strangely, that's a big defense too. There are some basic stuff like, what does the JIT do? Well, it takes this model of an application, your bytecode, and turns it into machine code. Used to be that bytecode might get executed occasionally, sort of like line by line, but we don't do that anymore. What we do is we take the bytecode as a model of your application, and it gets turned into machine code. And the machine code that we generate is different every single time, because JITs are optimizing, and depending on circumstances, it might generate this sequence of machine code, or this sequence, or this sequence. So your bytecode, even if the bad guys can compromise the bytecode, it's not the machine code that gets generated changes. So that doesn't work really either. So that's a good defense. When we load bytecode, there's a lot of verification going on to prove the bytecode does what it's supposed to do. And the JIT does some as well, because the JIT wants to make sure that this bytecode is going to generate valid machine code because it doesn't want to crash the system. So there's lots of checks and balances going on to make sure that the code is going to do what it says and nothing else, which is another defense, right? And then the last little bit is because some systems provide read-only memory segments, the JIT will make use of that and go, let's put the metadata, those constants, in places that can't be updated. So again, we shut the door on people coming in and changing static data, because if the JIT can prove it's never going to change, or if it's just constants, we can put it in places where it's even safer. There we go. And then there's the bytecode itself. Because you've got this stack-based machine, there is this process of obviously turning the bytecode into machine code. As I said, there's a register, but you can't access it. This really simple design, this is an example of bytecode. Anybody done any bytecode coding? Well, of course. Thank you, sir. Of course. It's a really simple stack-based machine. It's really simple. And you can't forge object references. You can't break out because the spec doesn't let you do things. You can't say, oh, take that object reference and add one to it. There's no language, no bytecode language to let you do that. It's a very simple thing. And it means that we can verify it fairly simply. There's lots of verifications we can do. So you may not realize this, but your bytecode gets verified. And if you want, you can turn the crank up and check it out. And it'll make sure that the bytecode you're loading isn't going to do random things, and ideally, eventually won't crash your system. But that's going on every time you load code, right? It's really hard to come up with a bytecode sequence that is vulnerable. It's not impossible, because there are always weaknesses. But again, it's not really a route the bad guys are going to try. Right. So some things we do, are you branching to the right places? Are you always making sure that data is initialized before you use it? Some basic stuff, but it's happening and you can't get around it. Well, actually, you can turn it off, but even if you turn it off, you don't turn it all off, because some of this stuff is intrinsic. We will check things because, bad things will happen. Right. So that's a load of stuff. There's more. There's a load more stuff. So next line defense, class loaders. Who's written a class loader? Oh, a couple. Oh, yes. Yeah. So class loaders are designed to keep code from different code sources constrained. And the idea is you can build a hierarchy of this. You don't have to have a hierarchy, but at the end of the day, a class loading thing provides bytecode to the JVM to do things with. And it gets used to keep packages separate, or it gets used like different versions. It gets used to keep code you're pulling in remotely separate, putting it in a sandbox. One of the original reasons was because of applets way back. So we keep a good track of the code that we load for you and segment it, right? And some systems, you can look at some application frameworks, will create so many class loaders. They get sort of excited and you have hundreds of class loaders, but they're all basically the same thing. They're all part of an application, a sort of system type thing. But if you don't do this yourself, you basically get three. You get a bootstrap one, which is for all those system classes. You have an extensions one. You've probably seen the extensions directory. You can put stuff in there and they'll get loaded ahead of everything else. And then you have the last one, which is the class path, which is the thing we all mostly use. The thing is, these are all specified on the command line. So that is definitely a target space. And there's nothing the JDK can do about it because we're assuming that your environment is safe. But there are things you can do. We'll talk about that in a minute. Okay. So one of those class loading things is remote code. Because though we don't do it very much now, it was the thing. Java came up because we could do remote class loading. Hey, I can pull code from somewhere remote dynamically and nothing bad will happen. And we realized that maybe that was a bit too naive. So anybody recognize this thing over there by the red arrow? Yes, yes, of course. Look, hands go up. Log4Shell, or Log4j. So Log4j, at its most worse, has a thing called a JNDI loader in it. So you have Log4j, you have JNDI, and JNDI was a wonderful tool that lets you load code remotely. And one of the things that has is called a reference object. And a reference object says, hey, if you want any code that you need that I talk about, here's the URL to get it from. So if a bad guy can get a reference object into your system, they can load whatever code they want. And nicely, we'll keep it in a class loader for you, so it's separate, but it can do whatever it wants. So if you ever find reference objects anywhere in your system, then you want to go and figure out why, because it's a bad idea. Right? So now I want to talk about something related to that, because you get to see. So the JVM itself has pretty good, strong defenses. The design allows you to assume that it's mostly safe, that it's really hard to compromise. The one big way that people get in, which I've just touched on, is serialization. Okay? And serialization is used everywhere. And I have to say, I had a little bit of help. I helped code some of the serialization stuff way back. Right? And it's very fast. And even if you think you're not using serialization, you are. Something somewhere in your system is using serialization. Right? Because anywhere you find object input stream, well, look, here's a scan on GitHub. Not sure how old this is now, but you can find this everywhere. All that open source, all those dependencies, it's going to have a bunch of these things. So object input stream is how you read objects from a serialized form, right? And it's all over your system. This is the target vector most popular for people attacking Java systems, because they've just got to get into that stream. And this is a serialization form turned into a table. There's a whole bunch of stuff, but I want to talk about a couple of bits so that you understand. Okay? So there are things here, right? What you have to understand about serialization is it's self-defining. When you load data, the form of the data that you're loading is defined by the stream, not by the classes that you're loading the data into. So though the stream may see things like the name of a field, like hello, and the class name, they are not connected. Yeah. There's a name of a field, which is where I want to put the data, but the data I want to put in is here, whatever comes. And that means that I can, in the serialization form, that data that the bad guys can access, I can decide what I want to try and put into your system. So if I could compromise your serialization data in any of these places that it's being used, I can cause code to be loaded. Because all I've got to do, I can make it an int or an array or an object, I can actually, if I said, okay, there's a field in your class that's an integer, and I'll say, okay, or in this case, let's say a string, but my data stream says I'm going to load a class, in this case, com.badguy.foo, that class will get instantiated. Code will run. And when code runs, other code runs. So even though it may fail, as far as you're concerned, as far as the bad guy's concerned, it's a win, because they got code to run. And all they have to do is get into your serialization form. Okay? So this is a really, really good tool for the bad guys. And implements serializable, which is all these classes that make up this. 15 million on GitHub. You just can't escape this stuff. Right? And what the bad guys do isn't just trying to crack one. They'll build these things. These are called gadget chains. Can I build a sequence of objects that end up doing something bad, like getting to runtime exec? That's the classic thing that people are trying to do. And if you think that looks hard, it's not really, because there are tools out there like YoSerial that will generate these things for you. So serialization is the biggest weakness we have, and we continue to have. And log4j, log4shell, was all about exploiting serialized weaknesses. Okay. So what can you do? Well, there's some basic stuff in the JVM. There's like class filtering. Yeah, you can put some rules in, but you have to specify classes. There's a Java 17 made it more useful. It was a bit clunky, but it's all regular expressions. Put this in this file so that when the JVM loads, I know what the rules are. But you can imagine how clunky that is. Blacklists, whitelists, regular expressions. Okay, that's not really where the OpenJDK guys want you to go. They want you to go down this route. Modularity. Anybody use Java modules? Oh, I want to take a photo of that, right? Because nobody uses Java modules. But honestly, from a security point of view, Java modules, because of the way that they are loaded and kept separate, their whole idea is to encapsulate code so that they can't connect to each other. Because serialization at one level is about serialization weaknesses about finding out what's on your class path. And modules make that harder, impossible to do. Right? It is the thing you will see. The OpenJDK guys are putting all their efforts into security features based on modularity. And nobody here put your hand up. Right? Right. Well, there are other things you can do if you don't like modularity. You can use, well, actually, that's not true. You have to use modules. You can use JLink to take a modularized system, chuck out all the code that you don't need, and produce a small binary. Less code, less risk. That's a good tip, right? But of course, since you're creating your own little mini JDK, it's up to you to keep that updated. Anybody use JLink? No, of course not. Oh, how can you use JLink? You don't use JModules. Yeah, but this is a tool to help reduce your exposure. Okay, and if you don't like modules, which obviously most people do, there are other things. Anybody done jar sealing? Okay, so, was that a hand? Look. I feel like this, yeah, okay. What sealing does is it puts some constraints on where you load classes from. It basically says, if you load any code under these packages from this jar, you must load all code under these packages from this jar. So if a bad guy inserts a second jar with a replacement or an extension, it won't get loaded. Well, it will get loaded, and then when your real one gets loaded, there'll be this conflict and it will break. But the idea is to say, this is all the code there is and you can't override it. It's not particularly hard to use, but nobody seems to use this stuff. Right. If you still want to use serialization, then the only advice I can give you is have a look at using records. Because if you use record classes, there's no code. If there's no code, there's no code to execute. You can't build gadget chains if you just use records. The challenge for you is that you can change your code, but you have all these other code that you rely on, which you can't change because it's somebody else's code. But the best advice I can give you, apart from switching to modules. Okay, so running out of time, let's do some other things. There was a question about compile to native. Does compile to native make a difference? Swings and roundabouts. So there's a bunch of stuff you can say it will give you from a safety point of view, because obviously you don't have a JVM anymore. You've compiled it auto native. There's no bytecode. Reflection is basically disabled or programmed in, so you know exactly what you're going to do from a reflection point of view. That's a very good safety point. From a negative point of view, you now have a fixed memory layout, so people can figure out where your password objects are because they're usually laid out in the same place. There is verification. Happens at the build time, which is good. So there's a plus. Not all the vulnerabilities are serialization and reflection based, so you don't get away with everything. There might be logic failures, but you know, from a serialization point of view, it's going to help make a big difference. You have a performance challenge because this compile to native gives you one level of performance. If you use the full JVM, you tend to get re-optimization, so you tend to get slightly better or sometimes much better performance. Right? And this all sounds very nice, except for the fact that bad guys can sometimes get into your build system. But that's a problem on both sides, really. Okay. So, 10 minutes. There are two other things that we hardly ever talk about, right? So the first one I want to give you is this one, Maven Central. Who uses Maven Central? Yes, hands up at last. Okay, right, so I'm going to flip through this, right. Malware, you've heard about it. It turns up all over. This is Python malware. It turns up all over the place. Doesn't get into Java. Because if you look at the different types of attack that happen, and again, I'm going to skip over this for time, but really, there's sort of several ways they get in. They're like, can I figure out that you typed in the wrong, you made a typo when you put in left pad, you put one too many Ds or something. If I can register that domain, and I can put up that code in Maven Central, then you could pull down the wrong thing because you made a spelling mistake. But that doesn't really happen very often because that costs money, and bad guys don't like spending money. Right? But it happens in other places. And then the other one is the version confusion, which is things like, I want latest. In Maven Central, you cannot publish anything on Maven Central unless you own the domain. In other repos, it's possible for, I can publish foo.1 and you can publish foo.200. And the consumer goes for the latest and they get somebody else's, not my code. Right? So those are sorts of things. So what Maven Central does, it says, no, you can't publish things you can't preview on the domain. Right? And we verify, scan all the files that get uploaded so that we can tell you whether they've got vulnerabilities in. And we're adding a bunch more stuff to it too to give you more information for making your choices. Right? So from this point of view, typo squatting is fairly reduced. Dependency confusion, if you use Maven Central, is gone because it's impossible. And we're working on the bits in the middle, which is to give you more information about the open source projects that you choose. Okay. So Maven Central is one secret weapon. The last one, that's you. Yes, you. I was going to say, who here is here? But I'm sure people won't put their hands up. Okay. Because you're not good at this, are you? Log4j. I'm sure we all had that fun of Log4j turning up and, I know, it was great for me because I'm in a security company. It was like, hey, something to talk about. But actually, it's a nightmare. This shows you that even today, whatever we are, 18 months later, 33% of the downloads from Maven Central are for vulnerable versions. And the biggest single thing we could all do to make Java safer for yourself is to manage your dependencies better. Because that's the vector they get in. And when we do the data analysis, it turns out that pretty much every time there's a vulnerability, there's a fix. So the challenge isn't that the fix isn't available. The challenge is that as developers, we're not applying the fix fast enough. So actually, the biggest challenge in the Java security space right now lies with you. You and your organizations are not applying fixes fast enough. Right? And it's slightly more complicated because when you say about applying fixes, it's also about your choices. What dependencies do you choose? And you tend not to pay much attention. Picking the latest version. Picking the latest version is not always the right answer. So there's all sorts of data out there. Move on. And there are all sorts of things happening for us to figure out how to give you the best insight you need to make those choices. So Linux Foundation, I'm working with the Linux Foundation on these things to help codify what makes a good dependency. Not just from, hey, the vulnerabilities, but also what the behavior of the open source project is. Right? Because if they have good developer hygiene, good security hygiene, they're a better choice. Right? And what you'll see on Maven Central now is you'll see this occasional safety rating. We're working that through right now. So Maven Central is going to give you more information for you to make these better decisions, right? And since I'm promoting Sonatype right this second, if you want to have a look at your dependencies and you want to start getting into things like SBOMs, anybody heard of an SBOM? Go. Yeah, this is good, right? So more SBOMs and modules. SBOMs are part of the story. It's another talk. I'll let you go do the digging. But bombdoctor.sonatype.com is a free tool. It's connected to Maven Central, but you can go play with it. You can visualize your dependencies and play with them and see what we think, how we're scoring it, what vulnerability is available, and as we try and figure out what's the right way to give you that advice. It's a fun thing. Yeah, and the rocket launches or doesn't, depending on how good your application is. Okay, look at that, whirlwind. I actually have 4 minutes left. Thank you for listening. I'm sorry it was a whirlwind stuff. Are there any questions? Okay. No? Okay, cool. Well, look, I have a bunch of stuff if you're interested, things we're doing. So obviously Maven Central and the new skin. We'd love feedback. We want to know whether it works for you. Bomb Doctor is this place for you it's this tool to go try. DevZone is Sonatype's developer zone. And then Fuji is where we're trying to put as much information as we can. If you haven't joined Fuji.io, I would encourage you to, because it's a vendor neutral place. Everybody's coming together to try and build all the information you need for you as a Java developer, whatever it covers. We're trying to put it at Fuji. You'll find everybody there. Oh, and lastly, the Malware Monthly. If you're interested in malware and what it is, basically not for Java, then there's some stories there. Okay, and I think I'll stop there then. Thank you very much.